Today I'm gonna work on one example. Um, then we will talk shortly about stress concentration factor because we are gonna talk in detail on chapter 6 area covering fatigue, but we just introduced stress concentration factor. For now, then we finish the beams by covering the curved beam. So we looked at the straight beam. So far, we are gonna look at the curved beam when it's under loading. Then we finish chapter the beams and we start cylinder and Wednesday class. Suppose we have this mechanical component, it's a crank. So this crank has a crank arm which is under force of F, and F is 300 pounds. So this is the magnitude of the force. It's applied at the distance of 1.5 inch from point C, and the other dimensions are given. And the diameter of this shaft is 0.75 inch, and this shaft has been fixed to the wall. So we would like to do two things. First, we would like to draw a free body diagram for these three components. Beam CF or component CF, component BC, and component AB. Draw the free body diagram. And AB. And after we did that, we would like to find the stress at point A of shaft AB. So point A is going to be this point. We would like to find the stress at that point. Why am I doing the free body diagram? Because if I want to design component CF, component BC, and component AB, I should know what would be the stress applied to these components. Then we can do the design, or if we want to do analysis, we can do that. So I will do component I will do the free body diagram for component CF and BC. Then I'm asking you to do the free body diagram for component AB as a class activity. So I will start with component CF. Component CF is going to look like this. Axis Z, axis Y, and axis X. One force with the magnitude of 300, it applies at the distance of 1.5 inch. So this is point F, this is point C. So at point C, I will see one force in opposite direction because the summation of the force should be equals to 0. So F would be 300 pounds. And what else I will see at point C? I will see that this force has a distance of 1.5. It's making moment about this axis, which is Y. It's making about Z-axis. It's making the rotation about Z-axis, and it's gonna be negative because first it's making a clockwise. Second, if you just put your finger in the direction of force, and your thumb is gonna show the direction of the moment, which is gonna be negative Z direction. So MZ would be 300 times 1.5, which is 450 pounds inch. So it's gonna be negative, so the reaction should be positive. So it's making positive mz at point C, positive 450. So point C is gonna see F in y direction, F in y direction, 300 positive J, and it's gonna see the Z moment. About z-axis, it's going to be positive 450 in the direction of k. So it should be to make positive rotation. So these are the only forces and moment applied to point C. One force reaction at this point and the moment at point C. So for point C, at component BC, point C here is gonna see these two force and moment. Point C at component BC is gonna see the negative value, negative 300J, and mz is gonna be negative 450K. Action and reaction. This point belongs to component CF. This point at the same time belongs to component BC. So it's gonna see the opposite force reaction. So I just changed positive to negative and this positive to negative. So for component BC, if I draw something like this, this is x-axis, this is y-axis, and this is z-axis.
Are they both ending at BC, or should the first column be CF?
Thank you, BF, CF. Thanks. Now let's look at component BC. At point C, I have negative 300. And negative mz, rotating about clockwise. So if you just put your thumb in the direction of rotation, your fingers, your thumb should go in the negative direction of z, which is this. So it's the reason that I put the arrow in this direction, not this direction. So mz. So this force acting here, the opposite force at point B should apply here is 300 pounds. So point B at BC is gonna see Fy equals to its y direction positive 300, y direction. This moment is applied here. Negative 450 in opposite direction should apply here. So it should be in positive direction. Mz would be positive 450. What else? This force has distance from point P, from the acting point. There is a distance between the acting point of the force and point P. So it's making moment. The moment is going to be about x-axis. The force is about y-axis. The distance is about z-axis. So it's making moment about x-axis. It's making clockwise. The mx would be 300 times the distance is 4 inch. This distance is 4 inch. So it's making clockwise or negative direction, this direction. So the moment that we are gonna see here, it should be positive. So it's gonna be in this direction. Mx is gonna be positive direction, 1200 pound inch, and it's about x-axis. I positive. So far, so good. It's just an example to show you how you can do the same process for any other mechanical components problem. This is how you can you draw the free body diagram for each part of the component and do the stress analysis at the end. Before we go through part AB, this is axis X, axis Y, and axis Z. Point A, point B. Point B at AB is gonna see the opposite. If Fy would be negative 300 and J MZ would be negative 450 in K. So it's gonna be this direction. My thumb should go in the negative. My finger is showing the direction of rotation. So MZ 450, and we have MX, which is negative 1200 in I. Negative, so it should be in this direction. So before we go through the class activity, let's look at component BC. I would like to look at these moments. The axis of this component is z-axis. So any moment in z direction is gonna make torsion. So it should be considered as a torsion. And any moment with the different direction is gonna make the bending moment. So this one on component BC is gonna make bending moment, but Z is gonna make the torsion on that. So if I want to find the stress at point P, I know that this one is gonna make torsion and this one is gonna make the normal stress. Now, do the same thing that I did for component AB and find the reactions at point A. Point A is the point of shaft A. This point, I mean. Number 49. I mean, the timer was not working, I just used the other one. I'm asking for a reaction at point A. Pardon?
I was reading the question.
Okay. Number 4. Would you come and draw? I mean, I'm not necessarily looking for a correct answer. I just want to see what would be your approach, or what kind of difficulty you will see on facing this problem or any other. Do you want to work on this, or? Jan, where are you? What do you think? I mean, just so we have negative 300 here, so it should be at least positive. The summation should be equal to 0. So m Fy is positive 300 in J. So this moment, whatever it is, negative 1200, it should apply in negative sign. So m x is positive 1200 I. This is x, this should be I mean. And this one, mz is gonna be positive. This force, I covered this moment, and this force. The only thing left is this force has a distance from point A, so it's making moment. It's trying, this is in y direction, this distance is x direction, so the moment is not in z direction. Y, x, the other one is going to be z. So it's making in this direction, which is negative m z. 300 times distance is 5 inch, 1500. in z direction. So it's going to be negative. So the moment that I need here is going to be positive 1500 in k. So these two can be added up. So I'm going to have mz 1950 in k. So 1, 2, 3. So these three forces and moment applied to point A at the end of shaft AB. Yes. Because I have two vectors, both are moment, and both acting in the same direction. I can add them up. So one force, one moment, and moment number one, moment number two. Any questions so far? Everybody can see how did I come up with this 1500K and why it's negative? Force times distance is making clockwise rotation. So clockwise is negative. Or just put your thumb in the direction of rotation. It's going to try to rotate in this direction. So your finger is going to be negative direction. Make sense? Why it's mz? Because force in y, distance is x, the moment should be the other one, which is z. Say it again. Both would be in positive. Can you see why this should be positive 450? Because here we have negative 450. So at the other end, if it's not negative, if it's not positive, it's going to rotate. The summation of the moment should be positive. It should be 0 for the component. So if I ask you to draw the force and load on the cross section attached to the valve, not to the shaft. So point A is going to be here. Whatever we have here, just change the sign and put for point A at valve. Cross section A, I mean. Fy would be negative 300, mz would be negative 1950K, and mx would be negative 1200. Good. I mean, this can be exam problem. I can give you a mechanical component like this, asking you to do the stress analysis. To do the stress analysis, you need to know what kind of moments, what kind of forces applied to the critical section. Then you can start calculating the stresses. And here I ask you to draw free body diagram for all components, but I could ask you to design, find the critical section. By looking at this, section A has the largest distance from the force applied here. So most likely section A or this section is going to be the critical section because it's going to generate the greatest moment because of this force, because it has the greatest distance from point A. But if you want to design each component, you need to draw the free body diagram for each component and start the analysis. Now back to second part. We would like to find the state of stress at point A of shaft. These are the forces applied to point A. Now we would like to find the stress at this point. So this moment is applied about x-axis. The axis of this shaft is x. So it means this is kind of torque. Z is not the axis of the shaft, so it's going to be the bending moment. And this is a shear force. Let me sigma x, the normal axis is x, so the normal stress is going to be x. It's going to be mz times y divided by iz. So if I look at the cross section from this side, this axis is going to represent z, this axis is representing y. So point A, if point A is here, do you think it's going to be tensile or compression at point A? At point A on the top of shaft, AB and the top point. Am I going to see the tensile stress or tensile? It's going to bend like this. So the upper sides of the neutral axis is going to be tensile. This side is going to be under compression. So M is 1950, Y is R, IZ is pi d power 4 divided by 64. R is d divided by 2. It's going to be 1950 times 32 divided by pi d power 3. The diameter is 0.75. You will find the bending moment, which is normal stress to the bending, which is 47.1 kpsi.
Wait, Dr. Gapi, on the denominator there, should that be a pi, not a 32?
Thank you.
Okay, that makes more sense.
So it's going to be 47.1 kpsi due to this bending moment. So this moment is going to make the torque. So it's going to be torsion. Shear stress is, if you recall, it's going to be T times C, which is the half of the diameter, divided by J. T times D over 2 pi D power 4 divided by 32. For now, I'm just writing this, but later I'm just writing 16 times t divided by pi d power 3. So it's coming from this. So 16, the torque is 1200 divided by pi d power 3.75 power 3 is gonna be 14.48 kpsi.
So when you solve out these equations, you're gonna end up with it in PSI and then you convert it to KSI?
Yes, it's basically you will get something like 14,480 psi, which is 14.48 kpsi. Yes.
When we do the sigma of x, it's positive because the torque in the bar is negative, so they cancel?
You mean this one?
Yes.
MZ is positive.
Are we talking about point A, the
On the
moments
shaft.
of forces at
Shaft.
B or at wall?
At the shaft.
Because the wall is positive, so does that make the shaft negative at the same spot, and they cancel the negative in the equation?
It should be how can we explain this, because it should be positive because it's under tensile, but how can we explain this negative sign? Say it again. So either y or mz should be negative. Because I is going to be positive. So, but none of them are negative because y is positive and mz is calculated. But this A is on the bottom. I mean, they are the same but in different components. Action and reaction.
Yeah.
Something. Let me pass on. I even me I got confused why it should because it's obvious that this point is gonna be under tensile because this is gonna make bending, it's gonna make A be like this. So any point on the top is gonna be under tensile. But the equation we could find mz positive, and y is positive, obviously. So how can we explain this negative sign here?
I think it should be positive. I just wanted to make sure because the equation starts negative, and I wanted to know why we canceled it. It's just because the signs in the
There should be
torque,
some
right?
explanation. I mean, because we should use the negative, but since I knew that point A is gonna be on the tensile, I just
Okay.
removed that. But it's not a right approach.
So because we're calculating it with a force instead of a reaction force, or because that would determine the sign, and then if the equation was negative my over I, that would cancel out. It's two negatives would make positive.
Yeah. But we should look at point A belongs to the shaft, not point A on the wall. So anyway, we should.
Yeah.
Okay. I think I got. So this force is making negative mz. True. Negative mz about this, but the react at point A we should have positive mz. Okay. If I want to find the reaction at point A, but on equation that I use negative mz times y divided by iz, this mz that I plug in is whatever moment this force applied to this point, which is negative value.
Okay. Cool.
So basically we don't plug in the moment coming from point A. We are plugging the moment that this force applied to point A. So just one side
Okay.
is gonna be. So for now, I mean for future, if you want to use this equation with the negative sign, just see what would be the moment that this force applies to point A. It's gonna be negative mz. So this negative is making positive.
All right.
Fair
Thank
enough.
you.
All right. Let's continue on this. 14.48. And if I ask you what would be the direction of torsion, just look at the look at mx is making torsion in this direction. So point A is gonna go in this way. It's gonna rotate shaft AB in this direction. So if I ask you for point 2, it's gonna be downward. For point 3, tau, it's gonna be this direction, and for point 4, it's gonna go this direction. For point 8, tau is gonna be this direction because the shaft is rotating in clockwise direction. So the tau is applied in x plane in the direction of z. So tau xz is gonna be this. Tau xy is gonna be the same value, but it goes downward. Now, if I ask you to find the principal normal stresses, we can do that for point A because you have shear stress, you have normal stress, you can find sigma prime 1 and sigma prime 2 by using this equation. So sigma y equals to 0, tau is going to be 14.48, and you can calculate for that. Any question on this? So I did based on the moment and the forces applied to that cross section, I could find the normal stress and shear stress at point A. Now, if I ask you to find the stress element at point 2, what would be the difference? So I'm looking for normal stress and shear stress applied to point 2.
So X is coming out of the board. Which is weird because it's not in the plane of the wall.
Number 31. Let's start with normal stress. What do you think?
Would it be MX times
It should be mx.
Yeah.
I mean, the only moment, mx is making torque. So in entire of this cross section, any point, it's gonna see this as a torque because x is the same as the axis of the shaft AB, and this is gonna make the bending moment. So if I change the points, the mx and mz are not gonna change. So the only thing which is different, this mx and this mz are gonna make different normal stress and shear stress. Number 11. Where are you? Okay, what do you think? Again, the moment, force, they are not changing over the cross section. All points in cross section, they will see the same thing. But different points, they are gonna see different normal stress and shear stress. Point 2 is located in neutral axis. So this MZ, it doesn't make any normal stress applied to that. So it's going to be 0. Shear stress, what would be the radial distance of this point from the center? It's going to be again half of the diameter, so it's going to be the same direction, same value, but the direction is going downward. So it's going to be tau xz, 14.48. I was looking for this force. This force is the shear force, is making transverse shear. it's making maximum transfer share in any point in this line, where point 2 is part of that. Tau max transfers for circular cross section is 3/2 V divided by A for circular. Force is 300 divided by area pi 0.75 squared divided by 4. 905 psi. So what would be the direction? The force is acting downward, so it's making the same direction of the shear stress at point 2. So it can be added to this 0.0905. It's gonna be 15,385 kpsi. So again, when you find the loads applied to the cross section, it's gonna be the same for all points in the cross section. The only thing which is different is the stress due to those loading. If it's located on a neutral axis, you don't see any normal stresses due to the bending moment. For this point, we don't have any transfer shear because we have covered that the first moment of area is 0 for point 8. But for point 2, it's going to be the maximum, and we can find the value, which is 1.5 times V divided by area. Any question on this? I was planning to finish 2 more topics, but it seems the examples took longer than others. Alright, I will finish those topics on